now guide you through the second step of the machine learning for floods practical example. In the first notebook, I showed you how you can train a flood extent segmentation model with the ML4Floods Python library and the World Floods benchmark dataset. The second step is now the inference process, where we apply a pre-trained model in order to predict the flood extent of given Sentinel-2 images. So we are in week 6, where we show you machine learning applications related to climate, and the specific practical use case showing you the ML4Floods project is under the topic number 6F. And we are specifically in this folder. You see in this folder 3 notebooks, one notebook related to training, the second notebook related to inference, and the third notebook providing additional helper functions that are needed for the ML4Floods practical case study. This workflow now introduces you to the second step after the training process, where we run inference of a flood extent segmentation model using Sentinel-2 images. It guides you step by step through the inference process of a flood extent segmentation model. We will load a pre-trained model from the ML4Floods project, and with that model we will then make predictions on a new provided Sentinel-2 image. The data this workflow makes use of are the following. So we use Sentinel-2 images that we want to have classified with the help of the pre-trained model. Then we have ground truth images classified in 6 classes instead of 3. So it offers additional 3 classes, and a permanent watermask created by the Joint Research Center, which is used for comparison purposes. And all data are available as part of the ML4Floods project, and if they are not available, they will be downloaded to your workspace. But for this training course, all the data is already available in the folder Tips for Inference. We start as we always start, so we load a set of Python libraries we make use during the workflow. One library this workflow makes use of specifically is the ML4Floods Python library, which is a key part of the ML4Floods project. And this is what we do here. We also run a set of helper functions, which you can have a look at. So you can open the functions notebook, which is also part of the same folder, and you can have a look at the specific functions that are available, and you can also see what these functions are doing. But we also explain in the workflow the respective functions if they are applied. So the first step is to load a configuration file, which is provided as part of the ML4Floods library. And this configuration file helps us to specify a specific experiment number which we are interested in, and this experiment number provides us a pre-trained model. And the experiment we are interested in has the name WFV1_UNET. And the function get_default_config from the ML4Floods library loads the JSON file which provides specific configuration settings related to specific data parameters and also model parameters. And we see here in the configuration file that the max tile size is set per default to 256, but for environments with constrained memory resources, and specifically also for the training environment, it is recommended to better set this parameter to 128. And this is what we do here. So we specify the maximum tile size under the model params group, and we set it to 128. The second step is then to load a pre-trained model that is made available as part of the ML4Floods project. So the next step is then to load the pre-trained model that is available on a Google Cloud Platform storage bucket, and we specify the link to the model we are interested in. So we set the model folder in the configuration file, and now we have to set the parameter test under the model params group to true, because now we are not interested in training a model, but we are interested in running the inference process, so in testing a pre-trained model and predicting with the pre-trained model. And this is why we have to set the test parameter to true. The next step is then to use the function get_model from the ML4Floods library, and this function loads the pre-trained neural network model, and once it is loaded we can print the model, and the printout shows us the architecture of the pre-trained model. And the model we loaded here is UNet, and this is a different model compared to what we trained in the first step. So and for this reason we also have a different architecture here. So we have quite a few more convolutional layers defined with activation layers in between, but still at the end the last layer provides a convolutional layer with 3 neurons as outputs, and this number of neurons resembles the number of classes we're interested to classify. And now, before we can perform the inference step itself, we have to load the model inference function. We can use the function get_model_inference_function also as part of the ML4Floods library, and this function allows us to conduct the inference process on images that are larger than 256 times 256 pixels. And this is important because the Sentinel-2 images are larger than the defined window size by the World Floods benchmark dataset. And this is what we do here. So we apply the function get_model_inference function, we provide the model, the configuration parameters, and we also set the apply normalization keyword argument to true. And the next step is now to load data we want to run the inference process on. And the data we use for this are Sentinel-2 images. So the next step is to load the data required for the inference process. And data we need for this are Sentinel-2 image files, but also ground truth data and a permanent watermask, which we use for comparison purposes. And the data has already been downloaded and is available in the tips for inference folder. But if you want to reproduce the example on your local machine, this code block here checks if the data is already available, and if not, then the directory is created and the images will be downloaded to the specified directory. And then we apply the function read_inference_pairs, which takes the variables defined above, downloads the data required for the inference process, and returns the data as tensors that can be passed to the pre-trained model. So the function already processes the Sentinel-2 images into a format that can be understood by the model. And the function returns the following objects. It returns torch inputs, which are the Sentinel-2 image tensors, then the torch targets, which are our ground truth labeled flood extent classes, then the torch permanent water, which is a tensor that provides the information from the Joint Research Center permanent water mask, and transform, which provides additional information to plot the final predicted classification on a latitude and longitude grid. And this is what this function is doing, and the result are 4 different tensor objects. And the next step is now, so we now prepared everything. So we loaded a pre-trained model, we loaded the data we need for the inference process, and now we are ready to run, in fact, the inference process, to run the pre-trained model, and with the help of this model to predict flood extent based on a given Sentinel-2 image. So the next step is now to run the inference process with the help of the inference function, and we provide to this function the Sentinel-2 image tensor, and the output are the probabilities of each class for each pixel. So the output tensor has the shape, has 4 dimensions. We have 1 for 1 image, then 3 for 3 classes, so these are the 3 probabilities, and then we have the number of rows and columns, which the Sentinel-2 image we use here, it has 997 rows and 997 columns. And as a next step, we want then to select the final predicted class with the function argmax from the NumPy library. And this function selects the class with the highest probability as the predicted class. And this is what we do here. So we first select with the function argmax the final predicted class, and then we can apply the function plot_inference_set, which allows us to plot 4 images in comparison. So we plot the Sentinel-2 input image as true color composite and as false color composite, which highlights specifically water bodies. Then we plot the ground truth data and from the JRC water mask, and we plot the predicted classification, which we just predicted with the help of our pre-trained model. And this is what we see here. So this is the input image as a true color, as a false color composite. This is the ground truth information with many more classes. So we have land, flood water, permanent water, seasonal water, and also clouds. And this is then the predicted flood extent, including the 3 classes, land, water, and clouds. And as a last step, we can repeat the inference process on another Sentinel-2 image to see how the inference process or how the model performs also on different Sentinel-2 images. And this is what we do here. So we specify another Sentinel-2 image. We get the channel configurations from our config file. We run the read_inference_pair function, which results into the 4 tensor outputs required to run the inference process. We run the inference process with the functions inference_function, and as input we provide the input tensors, which are the tensors of the Sentinel-2 image, and then the output are the probabilities of each of the 3 classes. Then we select the highest probability of the output as the final predicted class, and then we apply the function plot_inference_set and plot the 4 different images as comparison. And so what we see here is another Sentinel-2 image as true color composite, as false color composite. Then we have here the ground truth data, combining ground truth and the permanent water class from the JRC. So we have 6 different classes here, and then as a final image, the predicted flood extent with the 3 classes, land, water, and cloud. And now we are at the end of the second notebook of the practical use case of the ML4Floods example. The second part introduced you to the inference process, which applied a pre-trained model on Sentinel-2 images in order to classify those into 3 classes: land, water, and clouds.